Okay, so now we're into a section where I'm just going to gather together some important trig identities. There are numerous identities that you can encounter in trig that'll help you with various computations that occur in different courses. So I'm just giving you the bare bones of the ones you'll need for calculus 1 and 2 here. If you encounter others, you can always look up like half angle formulas and that sort of thing. All right, so we already, okay, so first off, an identity is a formula that holds for all theta in a given domain, right? So there's no exceptions to it, right? So it's a truth. You can use it as a kind of inequality. You can replace one thing by another. That's the utility of an identity. All right, and so we already have a couple. We have the periodic identities and the symmetry identities for sine and cosine. And I can also put the ones in here for tangent, but you can always recompute those, so I'm not too concerned about that. But remember that the sine and cosine have a period of 2 pi, and so this is true. If you go around the circle any number of times, you get back to where you started. So the sine and cosine remain the same. If you want to add in here the tangent of n pi plus theta is equal to tangent theta, feel free. That also is true. Tangent has period of pi. And then in terms of symmetry identities, the sine is odd, the cosine is even, and we also prove that the tangent is odd. So you can add that one in here. Now we're going to add a few to this list. The first one that occurs all the time is something called the Pythagorean identity. And it falls right out from what the definition of the circle is. So if you give me any theta angle you want, right, we know that the point on the circle that corresponds to that angle is cosine of theta comma sine theta, right? That's how we defined the cosine and the sine. But remember, a point on the unit circle has to satisfy its equation. And so the equation of the unit circle, remember, is x squared plus y squared equals 1. And so in particular, if I put in cosine theta for x and sine theta for y, I get an identity that holds no matter what theta I choose. All right, so what we say is that the cosine of theta squared plus the sine of theta squared is equal to 1. That's called the Pythagorean identity. Now you won't ever see the cosine squared or the sine squared written like this. Typically what people do is they put the power above the actual cosine and sine part. So you're going to see this instead. That's just notation. When you see this, it means to take the cosine of theta and then square that. Same exact thing is true for all of the other trig functions, okay? But not the inverse trig functions. Don't be piddling around with that -1 and thinking it's a power, right? For just basic trig functions, the power is typically written on the name of the function itself to avoid parentheses. All right, so we're going to add that to the list. All right. Here are some typical errors I see made often, right? And it's because people oftentimes don't think about what the cosine is doing, right? So when I say the cosine of theta, right, I typically suppress the parentheses here, but it doesn't mean they're not there, right? Cosine of theta is a function. So you're taking a function of a theta. You're not multiplying them. This is not cosine times theta, right? So you can't do that. It's the cosine of theta, okay? And furthermore here, when we look at like a quotient like this, you can't just kill the thetas, right? These aren't products. These are functions. And so it's sine of theta and cosine of theta in the top and bottom. Okay, so just a couple things to be aware of. For this your turn, you are just trying to identify if these statements are true or false, right? So we have identities that we know to be true. I want you to actually compare that to what you know to see if they're actually true or false. Okay, so try those and see what happens. All right, so the first one is true. Notice that instead of theta, I have a 1 over x in both positions here. And 1 over x is defined for any x positive. And so by the Pythagorean identity, I know that the left-hand side has to equal 1, right? The key here is that both these guys have to be identical, right? Excuse me, for this to work. Okay, this guy is not true. So to see that this is false, actually simplify the left-hand side by getting an LCD. The LCD is sine squared times cosine squared, because those are different functions. And so I need to multiply the top and bottom of this fraction by cosine squared of x, and multiply the top and bottom of this guy by sine squared of x. And if I then add the fractions, I get cosine squared x plus sine squared x over the LCD. And the top is 1, I agree with that, but the bottom need not be 1, right? And so if I can find an x value for which the bottom is not 1, then the whole fraction is not 1, and so this would not be an identity. So the counterexample I want, that's an example that if you plug it in, it shows something is false, right? So that's what a counterexample is. If I put pi over 6 in for x, I get this value, which is not 1. All right. For this guy here, this is false, right? If you want to use the Pythagorean identity, you have to square the sine and square the cosine. So even though the inputs are the same, the sum is not 1 unless you square those guys. Okay, you can actually check that on your calculator to show it's not 1. But that's the error that I intentionally made. We didn't square both. And this is false too, because notice, even though I'm taking the sine squared and the cosine squared of something, those somethings have to be identical in order to assure that I always get 1 back. And so for a counterexample, you can put any number of things in there. If you put in, let's say, pi over 4, that would actually show it's not equal to 1. All right. Okay, so let's actually look at this. The minute you have a handful of identities, you can often prove other identities, right? And so this one comes up often when you're looking at some derivative formulas and some integration formulas in Calc 1 and 2, right? So this comes up enough for me to actually look at it as a worked example. All right, so to prove this, I'm going to start with the left-hand side, say 1 plus tan squared of theta, and then I'm just going to manipulate that along the way using the definitions and the properties until I land at secant squared. All right, and so let's do that. Tangent of, I'm going to put in what tangent theta is. Tangent theta is sine of theta over cosine theta. But I'm squaring that quotient. The way you square a quotient is by squaring the top and squaring the bottom. So that's what I do here. And I'm going to combine these into a single fraction. To do that, I'm going to multiply this guy by cosine squared over cosine squared. So I get that. They now have the same bottom, and so I'm going to add the tops to get this fraction. But remember, we have a Pythagorean identity that tells us the sine squared of theta plus the cosine squared of theta is 1. So I get 1 over cosine squared theta. But here I can rewrite that as 1 over cosine of theta quantity squared, because I would have squared the 1 and the cosine separately to get this. But realize that the inside here, 1 over cosine theta is just secant of theta, right? And so indeed, 1 plus tangent squared theta is secant squared theta. That's another Pythagorean identity, right? All right, and then the other one that comes up not as often, but it comes up, is 1 plus cotangent squared theta is equal to cosecant squared of theta. So I'll let you work on that. It's exactly the same idea. Start on the left-hand side, plug in the definition of cotangent theta now instead of tangent here, go through the same process, and you'll get cosecant of theta. So give that a try, and then I'll put up the solution just so you can check yourself on that. Okay, so if you did it, here are the steps. Just make sure that you didn't make any arithmetic error, but those are the basic steps that you use to prove that identity. All right, now the next thing. This is a common sort of example that comes up in the calculus. Suppose you know that the cosine of theta is minus a fifth, and the terminal side of that angle theta is in the third quadrant. All right, so I have to specify that because technically, if I didn't specify this, your angle theta could have been in the second quadrant, right, where cosine is negative in the second and the third quadrant. All right, so given those two pieces of information, I want you to find the sine of what that angle is. All right, and so what you immediately do, if you know that's true, let's go to the Pythagorean identity, right, because we're trying to find the sine of theta, but plug in negative 1/5 for cosine. I square that guy and I subtract it from both sides. And then to find sine of theta, I take the square root of both sides, but don't forget to put the plus or minus. Remember, anytime you take a square root of both sides, you put a plus or minus. But now remember, this is where you have to use this second piece of information. The terminal side of theta actually ends up in the third quadrant. In the third quadrant, the sign is negative. And so the value here, I know I have to choose between these two. I'm going to choose the negative guy. So the sine of theta that I want is negative 2 root 6 over 5. All right. Same idea here, only now we're not trying to compute cosine, we're trying to compute tangent, right? But suppose we know the sine of theta is negative 4/7, and then the terminal side is in quadrant 3. All right. To compute tangent, though, remember tangent of theta is sine of theta over cosine of theta. So I'm going to need the cosine theta anyway. So I have to use the same strategy that I used in the previous example to compute that cosine theta. So let's do that first. Right, so I know this is true, and so I'm going to plug in minus 4/7 for sine of theta. If you square that, you get 16 over 49. Subtract that from both sides to get 33 over 49. And if you take the square root of both sides, then you get cosine of theta is either plus or minus root 33 over 7. But remember, the angle, the terminal side of theta is in the third quadrant by assumption. In the third quadrant, the cosine is negative, and so the cosine of theta is minus root 33 over 7. Good. So I now have the sine of theta and I have the cosine of theta. So by definition of tangent, I divide the sine by the cosine to get that guy over that guy. The negatives and the 1/7 cancel, leave me with 4 over radical 33. And if you want, you can write it in this form as well. Okay. Notice the process is the same. Use the Pythagorean identity, and then you use the definition of the other trig function to compute it. All right. For this guy, I want you, it's the same sort of idea. So you're given information about sine, and you now know that the terminal side is in quadrant 2. If the terminal side is in quadrant 2, right, the cosine is still negative. Okay, so keep that in mind. And you're going to use the Pythagorean identity and other identities, perhaps, to be able to simplify your results. All right, so give those a go, and then we'll talk about those in a moment. All right, so let's take a look at these. First thing we're going to want to do for any of these is find the cosine theta value, and then we can use it as we need to. Use the Pythagorean identity like we did before. I'm going to plug in 12/13 for sine of theta. That's what I'm given. Square it, subtract it from 1, and then take the square root of both sides to get plus or minus that root, which is 5 over 13. But remember, if the terminal side of theta is in quadrant 2, then the cosine is negative, and so I have cosine of theta is negative 5 over 13. All right, so that actually answers part 1, right? I want you to start off right, so you get negative 5 over 13 for theta. For tangent of theta, you don't need any additional computations, right? You need to simply know that tangent of theta is sine of theta over cosine of theta, and I have both those values in hand, so plug them in, and if you simplify, you get negative 12 over 5. For part 3, you're taking the sine of theta minus 4 pi, but 4 pi is a multiple of 2 pi, right? In fact, it's 2 pi times negative 2. And so we can use the periodic identity directly here to say that this sine of this value is sine of theta, and we were given sine of theta is 12/13, right? So there's no additional computation there. And then for the last one here, for cosecant of negative theta, by definition of cosecant of negative theta is 1 over sine of negative theta. But remember, sine of negative theta, sine's an odd function. And so sine of negative theta is negative sine theta. But I know what sine of theta is. That's 12/13. And so this value is negative 1 over 12/13, which you just take the reciprocal to get minus 13 over 12. All right, so these sort of computations you want to get familiar with, right? This kind of requires a comfort with these functions and the properties, as well as the unit circle to some extent. All right, so give these homework problems a try. They're all basically the same ideas of what we just talked about and let me know how that goes. Okay, bye.